we come to an important architecture for semantic segmentation. I write convolutional networks, that's wrong. I'm only going to talk about the UNet here as an important example. The UNet developed by Olaf Ronneberger and colleagues in Freiburg, and the hourglass network, which I think is essentially the same thing, developed in the US, have emerged as very reasonable architectures when the desired output is not just a vector telling us what is or is not in the image, as for image classification, but when we want to make a per pixel prediction. Such as, I'm going to show you lots of examples. Such as, for example, here these problems from cityscapes. You get some input image and you're trying to predict per pixel what is pedestrian, what is road, what is sidewalk, what is lamppost, etc., etc. And I am not completely sure now if we are looking in this image at ground truth or at the predictions that Daniel Kawecki, physics student like you, made 2 or 3 years ago. The fact is that this semantic segmentation is now extremely successful on problems such as shown here. Remaining difficulties are, for example, if you have a very big truck, then it might recognize that the front is a truck, but it might think the back of it is a house or a tram or something. So some of the top methods still may have difficulty with the very long range consistency, but by and large results obtained now are just great. Yeah? So there's an example of semantic segmentation where each pixel is mapped to one of the classes that you see here: sidewalk, wall, pole, traffic sign, terrain, etc., etc. Or another place where you need this is as an ingredient in pose estimation. So why would you want to estimate poses? Well, this is used in the consumer industry where you steer a gaming console or something like that. It is used in surveillance tasks, in many other domains. And as an ingredient, the current state-of-the-art approaches use networks that find, for example, all the left hands in an image and all the right hands in an image. So here already you ask the network to make quite some inference, not just hand, but left hand versus right hand. It asks, you have a neural network that finds all feet in an image and so on. So there you also have a semantic segmentation task, namely for each pixel the probability that it is a left hand or a right hand or a foot and so on. And then there's still the problem of cobbling these results together or to interpret them in terms of one or more skeletons. And that's a very interesting computer science problem in itself, which we will discuss later this semester. But as an ingredient, you do need these good semantic segmentations. And there are many, many other examples of where semantic segmentation is needed. Good. Now I've shown you here the famous figure from the original UNet paper. This is not exactly how experts like Alberto would recommend using them nowadays. I'll mention a few tweaks later on, but the big picture stays the same. Yeah? So what is the big picture? Well, that we have a U, hence the name UNet, and if it wasn't for these gray arrows here, we could have plotted the network more like this. And I think this is also what has given rise to the name of hourglass network. All right, and this should remind you of the picture that I have been showing of an autoencoder just a few minutes ago. Right? This, on the left-hand side, you would have the encoding network. On the right-hand side, you would have the decoding network. So in the middle, you have somehow a compact representation of your image content. And well, I call it autoencoding because here the output is the same size as the input. Now, obviously, here we don't want to use the UNet or hourglass network for autoencoding or for lossy compression, but instead we want to use it for semantic segmentation. So in other words, if I have 20 classes, then to make this a bit more explicit, here my input image, if it's a natural image, would perhaps be, let's say 512 times 512 times 3, where 3 comes from the red, green, and blue channels. And the output, if you want to do something like cityscapes, would be 512 times 512 times 20. Why 20? Because we have 20 classes of road, sidewalk, pedestrian, pole, wall, etc., etc. Okay, so for each pixel, we want to get a one-hot vector telling us for each of the 20 classes how probable they are present in that particular pixel. So this is one way of looking at it, but it turned out to be really crucial to not just, so when we draw architectures like this, what we mean implicitly is that the output of one layer feeds into the next layer. And you know, when I draw a thick bar here, these are abbreviations. Perhaps this here, I'm inventing these numbers now, but perhaps this here is 512 by 512 by 32, for example. Yeah, so 32 channels all arranged in one layer. All right, so if no arrows are drawn, then implicitly what this always assumes is that the output of one layer is fed into the next layer. Now we could become a bit more general. For example, we could say I want this layer here to receive not just input from the previous layer, but I also wanted to receive input from the original input image. So if the black arrows are first order Markov, then we could have red arrows, for example, for second order Markovianity. Or we could decide to have this higher order connections only within, this would be called a block of layers. We could decide to have these higher order interactions only within a block. Let me add another layer here to make the point more clearly. So we could decide to have not just these direct connections, but to also have second order connections and a third order connection. And what connection means, we will discuss in a moment. If I use all these connections here, then this is the idea in DenseNet. In a real DenseNet, we would complete all previous layers to all later layers. Here, perhaps we can call this a DenseNet block. All right, but what the UNet authors came up with were not these skip links or extra connections within a block, but the skip links that they came up with were these long range ones here, shown here in green. Okay, and rather than make the picture that I've drawn here, they have made the pictures, the picture that you see on the left. So here we have these skip links, which I also show now in the same color in green, between early and late layers of approximately the same spatial dimension, or layers of the same resolution at least. So let's look at this in more detail. All right, authors here start with input images that are 572 by 572 pixels. If it's a gray value image, it has a single channel. If this were an RGB image, then we would here have 3 channels. They now extract 64 distinct features from this at the same resolution. And from those 64 layers, they extract another 64 features in this layer. If you look closely at the dimensions here, they have used valid convolutions, so they did not want the boundaries to be tainted by zero padding. However, if you read Alberto's suggestions that we'll get to later on, he suggests to just use same convolutions here because it much simplifies the description of the architecture. Now at this point here, instead of max pooling, what they use is a transpose convolution. And that means it's a learned downsampling filter. So if you remember our downsampling lecture, we had a signal G, let's say a one-dimensional signal I'm drawing here. If I multiply it with a matrix, let's say this has 1 times n samples. If I do multiply it with an n by n matrix, well, then the result is going to be a signal H, which has the same dimension. But if I want to downsample, if I want a signal H, which is 1 times n half, then I need to use a matrix here which has n columns, but only n half rows. And if I give this matrix this generalized triplets structure, such that I have these bands here, then it is like convolution and downsampling. And this is what's meant by transpose convolution, and this is what's happening here. And this filter here, this smoothing and downsampling filter here is not something pre-specified, such as B-spline smoothing or something, but it is here learned. Good. So here now we have coarsened the image. This was up here we had the full resolution. Here we now have a representation at half the original resolution, and this is again a chance, now that we have fewer pixels to deal with, to increase the number of channels. So here the order suggests from going from 64 to 128 channels. The exact numbers don't matter or are something that can be optimized over. It's just the basic idea. Yeah? Then we again have transpose convolution here. Transpose convolution. Note that the number of channels increases again. Now it's already 256. And down here we have a really low resolution representation of the image. Here it's only 32 by 32 pixels, but up to 1,000 channels. So quite many channels. And then more transpose convolutions, this time to upsample. So to go back to high resolution. And now we come to these skip links. So what's the idea here? I've written it in words. The basic rationale is that here these images with low spatial resolution but many channels, that this is the semantic pathway. So down here, hopefully the network has understood what is in an image, what precisely, but because it's only represented at 32 by 32 pixels, the where is a little bit fuzzy. Yeah, so maybe in this cityscapes context here, the image is now very sure that it sees a tram on the left-hand side and pedestrians on the right-hand side. But if you imagine rasterizing this image here such that it has 32 by 32 pixels, of necessity, this is going to be a little bit crude. Now to inject again this high geometric precision, there is the second pathway, the geometric pathway implemented in terms of these skip links. Now these early layers here, you know, this is very early on, so these are still things like edge detectors, blob detectors. These early layers have not understood the difference between a tram and a pedestrian, but they are pretty sure about where one thing ends and where the next thing starts. And this information is now combined. You see, we have this arrow coming in, and we have that arrow coming in. This information is now combined in this particular layer here. Now, the way that the authors originally propose to do the combination is by concatenation. Yeah? So that, what does that mean? That well, you can think of it either as copying the early input over here, or you can think of it as, if we consider this layer, that its convolution filters will see as input on the one hand the blue thing here, but also the other much earlier layers. So concatenation is one possibility. The other possibility is to just sum up things of the same dimensionality. And in principle, you would think that concatenation is necessary and that summation results in a loss of information. And in principle, this is correct. But if you now look at the actual trade-off of how much memory it costs and you know, how quickly it runs on the GPU, etc., Alberto says that it turns out that actually addition is a good thing to do. All right, and you see that this coming together of information, well, it happens here, but it also happens there, and it also happens there. So we have the geometric pathway and we have the semantic pathway, and together they give us very good semantic predictions with very high spatial accuracy. So beautiful architecture, which I would say in this world has stood the test of time. So if a neural network has survived for 5 years, you know, that means it's really solid. So it's a very fast-lived field, and many of these recommendations change from year to year, but UNet has stood its ground for a few years now. Yeah, so congratulations. Good. Okay, maybe any questions right here? All right, so here are a couple of training hints. Use normalization, use residual connections, sum the features instead of concatenation, use larger kernels at the beginning and at the end. I cannot explain why. Use same convolutions because it's a bit simpler, and use the Adam optimizer instead of plain stochastic gradient descent. Now let's look at these first two. So I've been mentioning that, you know, 3 things made deep learning possible: the GPU, the training data, and the ReLU. And this is a bit arbitrary if I say 3 things, because there have been other tricks that were important. So for example, dropout was really important for a while, and dropout was superseded by methods such as batch norm. What does it mean? The pixels in blue are normalized by the same mean and variance, and this mean and variance are computed by aggregating the value of these blue pixels. Good. What do we see here? This is a schematic diagram where for a given layer, these are the channels, these are the samples present in the mini batch, and these are the pixels. Actually, you know, the pixels are shown here for completeness because it's a tensor, but since all of these blue regions always go from the very bottom to the very top, actually one could have omitted this pixel dimension from this figure here. And this figure now tells you that batch norm, which is probably the best known of these normalization methods, it looks at all the neurons in a given channel. So all the neurons, so for a given image, it looks at all pixels in a given channel, and it looks also at all pixels in the same channel for a second image and for a third image and for all images in the mini batch, and then computes a mean activation and a spread of these activations. And then it normalizes the output of that layer by this mean and variance. This is batch norm. Now, if you have a huge network, and a GPU with only 12 GB of RAM, then your mini batches are going to become very small. In the extreme case, your mini batch is just going to consist of one training image at a time. Especially, when you work with volumetric images, they are of course huge. Building averages over a single observation is not a very meaningful thing to do. So what these authors propose is instead this group norm, and that works very well in the limit of small batches in particular, where you now perform this normalization across a number of channels as opposed to across a number of images. And in their paper, they essentially show that a group norm never works worse than batch norm and often works better. I'm just mentioning this paper to show that there are many ways of normalizing. The best known one is this one here. Now you ask me, why do people do that? And I went back to the paper, and Ming, he's really one of the heroes of making deep learning practical. I mentioned earlier today the he initialization is the same person. And the paper says batch norm is known empirically to help improve the learning of neural networks. That's the only thing essentially the paper says on that topic. And other papers have been written trying to explain why batch norm works, and they say, yeah, it has a regularizing effect. But I would say honestly, it's not fully understood why batch norm works, and it's then even less understood why group norm would work. So I'm mentioning it again just to say that there are many open research problems. The practice of training deep networks has made huge progress, but the understanding of why or how these things help is still surprisingly limited. Good. So here, Alberto, who has a lot of experience training UNet, says definitely use some kind of normalization, but not before the last layer. Then it is within each of these blocks of layers at the same resolution, it's a good idea to use residual connections. What are residual connections? So this has also been invented several times under the name of highway networks, or there was a paper called deep residual learning, and it's also used in dense nets. So the idea is that when you have subsequent layers, traditionally each layer would only convolve outputs from the previous layer, and in these resnets, you add up this thing. Yeah? So what comes in through this arrow and what comes in through that arrow, it's at the same resolution, right? So it can be added up, just doing a plus operation, and that's it. If you want, you can also still use a linear operation on this one, and that is then called a highway network. And if you do that for each layer here. What this allows is some of the, well, the argument goes that this helps gradients flow to early layers much more easily and hence affords the training of much deeper networks. An extreme case of this is to have, the full Markovianity here, which would then be a dense net. That has also been a very influential architecture idea from Weinberger and colleagues in the last few years. Good, so these residual connections with or without an extra linear transformation have been super successful in making the training of very deep networks, or 50 layers, 100 layers, and so on, possible. Good, thank you very much.